Electronegativity is defined by Linus Pauling as the ability of an atom in a molecule to attract the bonding electrons towards itself. Now that's in contrast to a different property which is known as electron affinity. These things are not completely unrelated, but one is the ability of something to attract electrons towards itself in a covalent compound. The other one is a discrete, experimentally measurable quantity. Now, Pauling. What was Pauling up to when he came up with these electronegativity values? Well, these electronegativity values are actually based and derived from thermochemical measurements. So we cannot directly measure the electronegativity of an atom. But it can be inferred if you collect together lots of thermochemical data from lots of different compounds. And that's what Linus Pauling did. If you have a molecule of dihydrogen, it has a bond dissociation energy associated with it. What exactly is meant by bond dissociation energy? It's the energy to take a molecule of something like hydrogen and break it into two discrete atoms. Here we have a whole series of homodiatomic molecules: hydrogen, fluorine, chlorine. And you can see the bond dissociation energies there. You can see that those bond dissociation energies decrease quite quickly. The implication of this is that the difference in electronegativity between hydrogen and the halides decreases as you go down the group. The difference in electronegativity must be getting smaller because the difference between the predicted and the experimentally found bond dissociation energies is getting smaller. Now, how do you determine electronegativity? The formula that you will need is the one that I've presented here. First of all, electronegativity is given the symbol of the Greek capital letter chi. Chi A is the electronegativity of atom A, chi B is the electronegativity of atom B. So we're taking the modulus of this sum here. The modulus of the difference between the two electronegativities is equal to a factor here, 0.102. That is a scaling factor to reflect the modern units of kilojoules per mole. When Pauling was working on this, he was using the units of electron volts. So the modulus of this is equal to 0.102 times the square root of delta. Now, what is delta? Delta is the difference between the average bond strength that you'd expect and the bond strength that you actually observe. And if you plug that information into there, you can work out what the modulus of chi A and chi B is. So that just tells you the difference in electronegativity. If you do hundreds and hundreds of calculations based on bond dissociation energies, then that is the table of values that you arrive at. Electronegativity is not a perfect concept. It's not a directly measurable value with an absolute solution. But you can get trends in these things, and you can use that information very usefully to predict all sorts of things about your molecules. Those elements in the top left of the periodic table have very low values of electronegativity. Now, as you move across the periodic table, to the right-hand side of the periodic table has a very high level of electronegativity. There is a trend for electronegativity to increase from the left-hand side of the periodic table to the right-hand side of the periodic table. As you go down the periodic table, electronegativity is decreasing. Electronegativity is very high on the right-hand side of the periodic table, but also decreases as you go down. Why is there this trend that electronegativity increases from left to right across the periodic table? Well, the origin of that trend is the concept of effective nuclear charge. As you go from left to right in the periodic table, what happens? You add a proton and you add an electron. It also follows that because the effective nuclear charge is increasing, the electron affinities will increase. It becomes more favourable to add an electron to your atom. And the attraction of a nucleus for an electron is what we're measuring and what we're talking about when we're describing electronegativity. So because the effective nuclear charge increases from left to right across the periodic table, because the shielding of electrons of one another from the nuclear charge becomes less efficient, then all of these things follow, and in particular, electronegativity increases from the left to right. So effective nuclear charge increases because shielding becomes less efficient as you move left to right across the periodic table.